Right. So 131, let's go. Potential energy of a particle in certain field has the form U is equal to, okay, all this stuff. R is distance from the center of the field. Oh, find the value of R naught corresponding to the equilibrium position of the particle. Examine whether this position is steady. Okay, so yeah, fine. It's not that bad. The maximum magnitude of the attraction force. Draw the U of R and Fr of R, the projection of the force on the radius vector R. Well, first of all, I mean the theta hat thing. So both the other tangential directions, there's no potential energy. Sorry, there's no force in those directions, right? Because this guy's derived, right? Yeah, there's no force around that because it's like radially symmetric. So because of that, there's only the radial component of force. So this Fr is really just F of R. Yeah. Yes. So no problem, just do this thing. First, you want the value of R naught corresponding to equilibrium position. So whenever this guy's derivative is 0, so that will happen when you have negative 2 upon A, to A upon R cubed. And then you got positive B upon R squared is equal to 0. So basically, negative 2A upon R plus B is equal to 0. So basically, BR is equal to 2A. So R is equal to 2A upon B. R naught is equal to 2A upon B. That's the, yeah. Okay, and B is the maximum magnitude. And by the way, what's the second derivative of this thing? So yeah, like I mean, you have to figure out when the potential energy is the minimum, right? So the first derivative was just, oh yeah, I think this one too, because when you put this thing over here, what will this give us? Okay, first of all, just figure out what the second derivative is. So the first derivative was just negative 2 upon R cubed plus B upon R squared. The second derivative will be 6A upon R power 4 minus 2B upon R power 3. So take an R power 3 common, which will be 2 upon R power 3. And then you just got 3A upon R minus B. So when you put R as this thing, right, 2 upon B, what it really tells is it's going to be 3 upon 2B minus B. So it's like 3 up, it's just 1 upon 2B, which is positive, right? So this whole thing will be positive. And of course, R naught is also positive. So yes, it will be a minimum because second derivative is positive. So the graph will be something like that. Yes, makes sense, I guess. So, and since you just figure out the derivative is, your force is basically also, yeah, you got that. And what do we want? We want the maximum magnitude of the attraction force. Okay. Oh, okay. So the maximum magnitude of this quantity. Well, we already got the second derivative, right? This thing. So when is this going to be 0? It will be 0 when you just have 3A is equal to BR. So R is equal to 3A upon B. Whenever that happens, you will have a maxima or minima. And well, I guess it's going to be maximum because, yeah, that should be the thing. Okay, you could go for a second derivative, right? So that would be negative 6 upon R power 4 into 3A upon R minus B. And then the derivative of the inside stuff like 2 upon R cubed, and then you got negative 3A upon R squared. So now this thing is positive because this thing is positive. This is gone. This is a gone, I don't know. So that's not here. And this is positive. This thing is negative. So second derivative is negative. That means it's going to be the maximum value. Well, that makes sense. Yeah. So this really does give us the maximum value. So you just want to put R is equal to 3 upon B in there to get the maximum force, right? So into this thing. So F max. Oh, sorry, that's the second derivative. Sorry. Into this thing. So F max is just take that R squared out. So then that will just be 9A squared upon B squared, and then you got negative 2A upon R. Yeah, which is like negative 2/3 of B. Yes. Oof, yeah, and plus B right there. So that will be our force. And of course, this thing, where did it go? This is our original potential energy. Oh wait, actually force should be, it's not just the derivative of this thing, it's negative of the derivative, right? Oh yeah. So wait, but then the second derivative that we got was negative. So, huh, that's weird. So what happens when r approaches zero? Oh, so when as r approaches zero, this thing goes to infinity, and this also goes to infinity, right? Oh no, it's negative. Sorry. It should be like that. Okay. So the force here is just 2 upon r power 3, and then you got b minus 3a upon r. So as this approaches infinity, your force would approach negative infinity. You want the maximum force, right? Okay, you just want the maximum magnitude of the attractive force. Okay, so as, yes, like r approaches infinity and force is negative, so it's attractive, and its value is also, oh, it's not infinity. Sorry. Uh, uh, and when r is zero, right? When you're approaching zero, at that moment this happens. And no, it may or may not be attractive. Mm-hmm. When it's zero plus, this will be approaching negative infinity. Yes, and wait, but if it's zero plus, then r is in fact, yeah, okay. This makes no sense, but this is how it is. So, uh, this is the force, all right. You want the maximum magnitude, and also you want this to be attractive. What is this? So this guy's, when is this guy's maximum magnitude? We took the second derivative was something like that, right? So, oh sorry, this thing is the second derivative, and this is the first derivative, so it should be negative of that. Oh yeah, negative of this thing is the force. Yeah, and this thing is the second derivative. So clearly r is equal to 3 upon b would be the extremum value, and at that point, so yeah, it should be negative. That would make, like, this is also negative. This is the force, this is the derivative of the force. So when you put 3 upon b for this, so the derivative of that, uh, that's not good. Well, this is negative. Yes, it's attractive. Very good. Oh god, attractive. So it's a minimum value if r is positive, and it's a maximum value if r is, yeah, something like that, huh? Come on, think. This is the second derivative. This is the derivative of the force with respect to r. Now that just gives us r is equal to 3 upon b is the maximum value. Is this a maximum or it's a minimum? So you have to take the derivative of this thing to actually understand that. So we'll just skip that 2 over here and just, yeah, okay, no. What we will do is we'll take the derivative directly. So this will just be negative, so negative and negative, so 6 upon r power 4 into all this messed up stuff. So that goes to 0 anyway. And then other than that, you just have 2 upon r power 3, and then you got 3a upon r. So the derivative is positive, which means it's a minimum value, which is exactly what we want. So yeah, it works out. Over there, the maximum that we got, that when the negative of the force was at the most positive value, and over here force at the most negative value, which is exactly what we want. Yes, when r is positive, and of course there's only one extremum, so yeah. And yes, this is asymptotic because right, it was like r is, oh, r cannot be negative actually. Yeah, so you don't have to worry about a negative thing. And then as r approaches 0, right, this quantity approaches, oh, this is bad. So not this quantity, this quantity, that's the force, right? So if I take r square common, it will be negative. So just take negative inside actually. It's going to be 1 upon r squared into b minus 2a upon, oh wait, okay, that's negative, sorry. It should be 2a upon r minus b. So as r approaches 0, this quantity actually approaches positive infinity. So yeah, that will do it. It's not attractive at all. So really at r is equal to 3 upon b, we get the maximum attractive force. Yeah. So this is our force, right? F is equal to this, and F most attractive, which is like F minimum. Yeah, that is equal to, so you just put 1 upon r squared, so that will be like yeah, b squared upon 3, sorry, 9a squared. Why is this over here? This makes no sense. It should be 1 upon r squared and not anything else. This is wrong, sorry. And then from here you have 2 upon r, which is 2/3 b, and the 2/3 b minus b is just negative 1/3 b. So the magnitude is b cubed upon 27a squared. That should do it. So b cubed upon 27a squared. Yes. And also you want a graph. Oh, that's going to be hard to do. This is the kind of function that we're dealing with, right? So we know it becomes the minimum. So yeah, actually it should be negative anyway. So it becomes negative and minimum at r is equal to 3a upon b, right? So 3a upon b, it becomes that. And then at 2a upon b, this force is 0. This is the r. Okay, what we want is not this. We want the ur and this. Okay, what? The plots. Oh, as a function of r. Okay, that's what they mean. So this is our force. Sorry, this is our radius, of course, and then this is our force. So over here it's going to be 0. Here it's going to be repulsive and it goes to infinity. The potential energy as well goes to infinity, in fact. Okay, anyway, and over here it's going to be like that. And well, I'm guessing it can be 0 at some other values as well. No, it won't be. And from here, what will happen? So if r is bigger than 3 upon b, what really happens to this guy? That was when the derivative was 0, and then after that, yeah, like it will just keep on going, and then it will go asymptotically. So whenever r approaches infinity, f approaches 0, right? And let's just, I don't know, take some big value. So let's say 6a upon b, and then this will be 1/3 b minus b, so it's like negative 2/3 or whatever. So it's negative throughout, right? Whenever r is bigger than that, and yeah, it just becomes 0 when this happens. So cool. It's never positive. It's just below this, and then it approaches 0 as r approaches infinity. So it's got two kind of asymptotes. Yes, this asymptole and this asymptole. Cool. Just actually, you know what? Yeah, just use this directly. So the force is this. Yes, that's one graph that we need, and we also want the potential energy graph. Hopefully this will help. Okay, so when 2a upon r, at that point it will be extremum value, and we already got that that extremum value is when the potential energy is minimum, right? Yes, equilibrium position, and examine whether it is steady. Yes, it is steady because, well, it's just 1 upon r squared and it got a upon r minus b. So when you put r is equal to 2a upon b in there, what do you get? It's like a upon r minus b. That's what we're looking for. When you put that, you just get b upon 2 minus b, I guess. Uh-huh. So that's negative, and from that you can say your yeah, like potential is actually just negative, and it's a steady thing, whatever. That's not the way for it to go. What we want to prove is that the potential energy is actually minimum at that point. So look at the derivative, right? So the second derivative, it's zero right there because the slope is zero, and then this slope is negative right here, as you can see, and that means that um, yeah, it's decreasing. So this actually is like unsteady. Wait, what? That can't be. Oh, sorry, negative. Oh yeah, so this force is actually negative of what it yeah, it's negative du upon dr. So because this thing is positive and then it's negative, so the df upon dr thing is what am I saying? Yeah, df upon dr is negative, so actually second rate of potential energy will be positive. So it's actually a minimum value thing. Yeah, and it's also negative, and yes, that makes it happen. So something like that. And then over here, the slope will be negative, and then it goes to infinity as r approaches 0, right? Because it's basically like 1 upon r and then a upon r minus b. So as r approaches 0 plus this happens, and then as it approaches infinity, of course, uh, this thing approaches 0. Yes, yeah. After a certain point, it becomes 0. When does it become 0 really? It becomes 0 at r is equal to a upon b. Oh, it should be b, sorry, over here. Right, so at a upon b, so at 2a upon b, this thing is the minimum. At a upon b, this thing is 0. Man, why am I not drawing good today? Usually I draw good. It's just the graph is not looking good. Okay, draw it better this time. So you got some value over here, and then so now it's supposed to be over here. Right, I mean it's pretty steep actually. But anyway, that's what happened. And then at 3a upon b, so this point is just 3a upon b. At this point, there's an inflection point, so the concavity changes, right? So over here it's concave up, now it's going to be concave down at this point. I mean after this point. So like that. It's expected, yes. And then this just goes up like so. Yes. That should do it. So this thing is potential energy. And why is this? Yeah. Now it's good. Fine. Finally we got it. Let's go to 132 now. In a certain two-dimensional field of force, the potential energy of the particle has the form u is equal to alpha x squared plus beta y squared, but alpha beta are positive constants whose magnitudes are different. Find out whether this field is central. What does that even mean? So it's a two-dimensional field of force. The potential energy of the particle has this form. Those magnitudes are different. That's the main point. Okay. So the force is just, so it's like negative gradient of u. And what is the gradient of u, you might ask? It's just this thing. It's got negative, and then you got partial upon partial x of u, so partial u upon partial x. Then you got partial u upon partial y. Because it's just two dimensions, that's why only two of these. If this was a third dimension, you would add that as well. And this, don't get scared. This is just a vector. This is just a vector, right? It's just way of writing a vector. Similarly, I could just write this as negative, and then you got partial u upon partial x and partial u upon partial y. Well, of course, it's just partial derivatives, so no big deal, right? It's just negative of So partial derivative of u with respect to x, that will just be uh, 2 alpha x, yes. And then over here, we just have 2 beta y. Now, this guy's dot product with the radius vector. So the radius vector is just x comma y. So f dot r is, well, negative of uh, 2 alpha x squared plus 2 beta y squared, which is, I mean, okay, actually, that's not how it's supposed to be. No, that's not. Uh, but I really want to show that this is actually along the radius or not along the radius. I mean, okay, it's obvious that it's not along the radius, right? Because if it was along the radius, it would be something like a multiple of x comma y. That would happen if alpha and beta were the same, but it's not. So that means it's not central. I think that's what central means, that it's along the radius vector or opposite to it, whatever. I don't think so. So A probably not correct. What is the shape of the equipotential surfaces and also of the surfaces for which the magnitude of the vector force is constant? So the magnitude of the vector force, I mean, let's just call that like square of that. So, and divide by 4 as well. That will just be alpha squared x squared plus beta squared y squared. So if this is some kind of constant, I don't know, alpha squared beta squared times A, yeah, something like that. Then this would be x squared upon, well, beta squared, I'll just call this a squared. Beta squared a squared plus y squared upon alpha squared a squared is equal to 1, which is basically an ellipse. So B is got an ellipse basically. And also, what is the shape of the equipotential surfaces? So the potential energy, it was, sorry, potential, not energy. That was just of the form. Oh, actually, it is potential energy. Whatever. So it's just yeah, alpha x squared plus beta y squared. So that being equal to some kind of constant, right? That's also an ellipse, just with a different, AB value, or I should say AB ratio, or whatever. Yeah. So let's do A first of all. A has answer of no. B has, okay. So B, what is the shape of the equipotential surfaces and also the, okay, so equipotential surface, equipotential, but you know what, I mean, this is so trivial that we don't even need to give an explanation. We'll just say both are elliptical. So yeah, that's it, both elliptical. Next, 33, so 133. There are two stationary fields of the force F is equal to AYI and F is equal to AX. Okay, so two different forces, huh? Okay. Find out whether these fields are what? Are potential? What? What are these people talking about? You could say whether these fields are conservative or something like that, but are potential, what does it mean? They probably do want to ask whether or not these fields are like, conservative or something. It's dependent on what y value you have. So how do we know a field is conservative? So I read somewhere that it is conservative if its curl is 0, but I don't want to use that. Actually, that kind of does make sense. So if I go through a loop, right? So if I go through a loop, and I mean, of course, it's a dot product and everything. Yeah, and that should just give me 0 because the total change in potential, that should be 0. And then you can just make this loop be smaller and smaller and smaller. And you know that this loop is basically just a surface area, the surface integral of the curl. So like this, of the force, and that dot dA vector. I mean, okay, this is probably not what I should give you. What other choice do we have? That's the only, I mean, like proper way of checking whether or not this field is, I mean, conservative or not. And I don't know what we say, like fields are potential. What does it even mean? Fields are conservative, I understand that, but fields are potential. Uh, okay, I just want to prove that maybe these are not potential. So first we'll check using this thing. So we'll figure out if the curve is 0 or not. So for conservative fields, it must be 0. For non-conservative fields, it may not be 0. So first we'll talk about the curve of this thing. So it's just a y comma 0, and then you are doing partial upon partial x, partial upon partial y cross. So if you are a beginner level, just ignore this 133 question. I'm gonna leave it anyway if I don't understand what's happening. Okay. So I'm just trying to prove that maybe these are not, conservative. And I really don't know what fields at potential means, but we can prove whether or not it's conservative. Fine. So you got this thing, this curl. So the cross product of this is going to be, so with I and I 0, I and j is there. So it's just going to be 0 actually because that's 0. Then minus, so you got j times, it's like cross product, so it should be 0 times k hat. And then you got minus, and what was I saying once again? Yeah, because like j cross I, that is negative, right? Yeah, that makes sense. Oh, you could just think of it as a 3 by 3 vector, but with zeros added as z component. Yeah, that's something that you could do. So then you can do it, right? So we have a formula, I mean, easy way of doing this for 3 by 3 vectors. That is just crisscross, and this will be 0. Boom. Sorry, it should be 0 over here. And then once again, for y coordinate, just crisscross 0. And then for this guy, minus a partial y upon partial x. Oh, so there's no, oh, sorry, it's partial y. What am I doing? So it's just a minus a. And yeah, like this curl, it's not 0 all of the time because AB are constant, not necessarily zeros. So this probably is not. And using the same logic, we can say, okay, this might also not be 0. Yeah, right. Oh, it's slightly different, I think. It's got AXI plus BYJ, and over here you had AYI. So if this thing is AX and BY, then, oh, well, in that case, in that particular case, I mean, this is 0 anyway. These XY components are 0. And then for this guy, partial upon partial x of by, that is 0. And then partial upon partial y of ax, that is also 0. So, right, the second field is conservative and the first is not. Right, so now I want to prove that the first is not conservative in a proper way, right? So the way to do it is just to take a loop, right? Take a loop. Yeah, that should do it. What kind of loop should we take? The curl is not 0. Yeah. Oh, okay. It's along the x-axis, right? That's the thing. That's why it was not 0. You have to use that somehow. So, right. What would happen if I just went up? No work done. Okay. Then your y coordinate changed, and now I went like that, right? So the whole area under it multiplied by a, right? So if this is the xy axis, then this whole area multiplied by a, that is the work done. And then I went like this, no work done, and then I went like that. So negative of this work done. So this cycle caused this work to be done when I went throughout this square. Yeah, and that just means, right, this actually has this is actually non-conservative. So we can say Ay I hat is non-conservative. And then there's no such way of proving that this thing is, uh, this thing is conservative. But let me give you an idea. Whenever you go along x-axis, so if you go by, I don't know, x comma y, this kind of vector, right? Whatever is happening in the x direction, that is completely oblivious to whatever is happening in the y direction. So as you go through a loop, your y changing, it does not actually affect your, the integral in the x coordinate. So what integral I'm talking about? It's this integral, ax dx. So this is, I mean, a loop integral. And yeah, so it's not having that y term in there. So it's, as you go back to x in the end, I mean, this integral just goes to 0, because throughout this, let's see, throughout this little thing, you are doing ax dx integral from here to here, and then over here you are still doing the same summation, but now your dx is negative. So you have done the negative summation, and that means whatever value you got in this, you got the negative of that over here. So this in the end adds up to 0, and along these you're not doing anything. So that makes sense. So I cannot exactly prove how this has to be, but I guess that's good enough. I mean, it gives you idea of what's happening. But yeah, the proper way of doing it is to take the curl and see if it's 0 or not. And I really don't like doing that. But what other thing could you do? Because if it has to be 0 for each and every loop, then the only way for this to work is that the curl must be 0, so that for even the smallest of loops, this works. Right? 130. Oh yeah, I forgot to write this. That ax I hat plus by j hat is considered. I don't know what they mean by the fields are potential. Or maybe they mean like fields have potential or something. If they have potentials, then they must be conservative, right? Otherwise, it doesn't make any sense. Because, yeah. 134. A body of mass, something is pushed with initial velocity v0 up an inclined plane set an angle alpha to the horizontal. Friction coefficient equal to k. What distance will the body cover before it stops, and what work will the friction forces perform over this distance? Distance will the body cover before it stops. So, okay. I mean, you could just go by work energy theorem. So, if it is set with half mv naught squared, right? So half mv naught squared is initial kinetic energy. This will be equal to the negative work done by gravity as well as the friction. So the friction does work of negative g cosine alpha, and that times it's a negative mg. Sorry. And okay, I should not put negative. Just talk about magnitudes. Mg cosine alpha, and that times the length, which is, well, basically just h upon cosine alpha, right? Oh, sorry, h upon sine alpha. Yeah, well, that, or let's just go with L, where L is the length on the plank that it traveled. And then for gravity, just going to be mg per h, which is basically L sine alpha, right? That should make sense. And then finally, kinetic energy is 0 and everything. Yeah, cool. So you can definitely figure out when it's stop. What distance will the body cover? So L distance, right? L will just be v0 squared upon 2 times of, well, 2g, basically 2g of sine alpha plus cosine alpha, which is v0 squared upon 2 square root 2g sine of alpha plus pi upon 4. That should do it. So L is v0 squared upon 2 square root 2g, and then you got cosec of alpha plus pi upon 4. Next, 135. A small disk A slides down an initial velocity with an initial velocity equal to 0 from the top of a smooth hill of height h having horizontal portion, figure 1.30. Nice. Having horizontal portion. What? Oh, so like this, huh? What must be the height of the horizontal portion h? Oh, okay, so this little thing is the horizontal portion. Fine, fine, fine. To ensure the maximum distance s covered by the disk, what is it equal to? So what must this small h be? Right, if this thing is horizontal, it's just gonna be, yeah, it's like short like that, huh? So, oh, so its velocity changes, huh? One time required. Maximum distance s covered by the disk. So, uh, what is s? This thing is s? Fine, 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 fine. Let's do it. So when it goes down by h minus h, what kind of velocity does it gain? It just gains, uh, yeah, like half mv squared. This is called half v squared is equal to mgh. So just gh. It's gonna be g times of capital H minus small h. So its initial velocity, which was completely in horizontal direction, by the way, that's just like square root of 2g into h minus h. Okay, what is the time required for it to fall down? That will be when h is equal to half a t squared. Like this should be g actually. T squared, that should make sense. So t is just 2h upon g square root of that thing. So this times that, that's the displacement. So what s is square root. Okay, that 2 just comes out. So square root of h into capital H minus small h. Now it's pretty obvious that this will be maximum when small h is equal to capital H upon 2, right? Because, you know, AMGM inequality and everything. Yeah, so like this is less than or equal to h plus h minus h. And equality happens when both are equal. So to get the maximum value, which is basically just capital H, right? Your small h should be capital H upon 2. What is it equal to? Fine, 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 fine. So just call this thing H naught. I don't know. Or just call it as H. Yeah, is equal to capital H upon 2, and then the displacement is, so just capital H itself. Nice. Next question. 136. A small body A starts sliding from the height h down an inclined groove, passing on to a half circle of radius h upon 2, figure 1.31. Fine, like that. Assuming the friction to be negligible, find the velocity of the body at the highest point of the trajectory after breaking off the groove. Breaking off the groove, what does that mean? Inclined groove, passing into a half circle like that. Friction to be negligible and whatever. Find velocity of the body at the highest point in trajectory. It just starts sliding down, huh? Oh, okay. Now I understand. So this would have been zero if it just stayed over here continuously, right? So if this was in a tube, that is, it would go. But now what will happen is that at some point the normal is not enough, and instead it will just start flying around. That should probably happen, I guess. Yeah. Yeah, but whenever it does not, I mean, go away, what should happen? What is the velocity at this point? We don't know. Okay, what's the velocity at some, I mean, some height x? It will just be like square root of 2g into small h minus x. That's our velocity. So v squared upon, well, h upon 2, right? I'll just go with r, not h upon 2. So v squared upon r is equal to the square of this thing upon r. So 2gh minus x upon r. Now this acceleration is provided by, you know, the normal force, right? So the normal upon m, and then there's the gravity that's also acting. So if this thing is x up, right? So this thing is r, this is x. Oh, okay, this is obvious that it should be just fine. You know what? Let's just go with r. I don't know. I don't care. I'll just go with r. So this whole is just x. So then this thing's gonna be r minus x, and this thing is r, whatever. And then gravity acting in that direction. What you want is just the tangential, sorry, not the normal component, right? Yes, so it will in this direction. So, wow, this is getting complicated really fast. Draw a bigger figure. Radius along this. This is r is x. This thing is x. Gravity is acting in this direction. Just want the normal component. So what is this angle going to be equal to? This is going to be 90 minus whatever this angle is, and this is the same angle as that. What you wish to find is just g cosine of that angle. So cosine of this angle is just r minus x upon r. So g into r minus x upon r, that is what we are looking for. Right. So that acceleration is outward. So this actually has to struggle opposing that. So really normal upon mass is just 2g h minus x upon r, and also as it goes up, this actually, yeah, and right here is not happening. Yeah, that makes sense, I guess. This can only be pushed. It cannot actually be pulled or anything. So after whenever normal has no need for it to happen, it will just stop putting the force, and yeah, now the velocity will be so low that it will just stop going in that motion. You just fall down, something like that, right? So whenever it is moving, then this should happen. So this plus that, yeah, it should happen. So like minus all that stuff over here. This must be, oh, it should be negative, I think. Nah, it should be positive. And this has to be bigger than or equal to 0. Yes, that's for sure. So at what x value will this start to depart from the trajectory? That will happen when you got h plus r is equal to 2x. So x is equal to h plus r upon 2. Whenever it's bigger than this thing, it will start going away. H plus r upon 2. Well, in this particular case, r is just small h upon 2, so it's going to be 3h upon 4. Yeah. Oh, it's supposed to be 2 over here. Sorry. Okay, this is wrong. 2h plus r is equal to, wow, this is complicated. Okay, keep on going. What is that doing? Okay, 2h plus r is equal to 3x. X is equal to 2h plus r upon 3. At that height, it will fall off. Fine. And we just need to find the velocity of the body. At the highest point, okay, this is just, I can't believe it's that complicated. So at the highest point, just the tangential, sorry, the horizontal component, that's the only thing that we have to look for. Okay. For this case, r is just h upon 2, and just leave it like that, you know. Yeah, leave it like that. But you got what x is and everything. Once again, let's just draw that figure. So at some certain h, maybe like that, sorry, some certain x, and it's going like this. This is the velocity. We just want the want this component of this. So got r. This thing is x minus r, and I believe this to be. Oh, it actually is less than r, I think. So it's not even up. It's down. Okay. How can that be? No, that's pretty wrong. But how can that be? This should not happen. Huh? Uh, that's h and r is in this case h upon 2. So, oh, okay. Sorry. H in this case is it is 2r, and that's why it's 5r upon 3. So actually, it is above it. Yes, it's okay. It's okay. No problem. If it was less than h upon 2, let's say if small h was less than r, it would have not even got to that place and would just start going down, right? Okay, so now you have it. We just want this component of the velocity. So cosine of this angle, and this angle is same as which angle? This is tangential, right? No, I got 90 minus that angle, and this is the same angle, and this is the same angle. Yes, this angle is the same as that angle. So cosine of that is x minus r upon small r. Yes, that's what we're looking for. So this quantity, whatever the velocity is at that quantity, which square root of 2g into h minus x. Yeah. So we are looking for square root of 2g into h minus of this thing. Yeah. Minus 2h upon 3 minus r upon 3. And then the horizontal component of this guy. Right. That will be the velocity at that highest point. So the cosine of that is just x minus r upon r. This minus r, can you believe that? Okay, it's going to be 2 times of h minus r. And that upon r. Yes. Cool. So now let's put up the final answer. Or you know what? Let's just leave some parts right there because who knows, we might need them later on. Okay, all of that. So we'll just have velocity, the speed, sorry, at any inclination, at any height x will be this thing. X of braking, so let's call this xb, is 2h plus r upon 3. And velocity at braking is square root of what am I doing? Yeah, this is going to be just h upon 3, so it's h minus r upon 3. So 2g into h minus r, that thing upon 3. That should do it. Now, velocity topmost point, right? So I should just say horizontal velocity. Velocity braking horizontal, that is just square root of 2g h minus r upon 3, and that times of 2 into h minus r upon r. Yes, that's the whole thing. Okay, cool. In fact, just leave it like that because I guess this conveys the whole message it by itself. Okay, so what we were doing is they didn't give us any values, right? Oh, they did. They gave it as h upon 2. So you just need to find what this is. Right, we'll just say h is 2r to simplify our thing, right? Okay, that gone. It's just gonna be, wait, what? No, it's just r upon 3. Sorry. It's just gonna be r upon 3. Yeah. Oh, God. I guess it's correct. Oh, I don't remember what it was. Yeah, it must be. What else could be going on? And why is there this 2 though? Oh yeah, so it was just oh, it's sorry. It should be x um minus r and that upon r, right? So this minus r, that's going to be 2 into h minus 3 upon 3. it should be 3 over here. Sorry. Okay, that makes sense. Fine. And then you've got, well, 2 into r, and that cancels, so that's upon 3. Yes. Okay. And then 2r is just, well, h. So this just becomes 2/3 square root of hg upon 3. Yeah. Which is supposed to be 2/3 square root of hg, and that upon 3. Alright, next. 137. A ball of mass m is suspended by a thread of length L. With what minimum velocity has the point of suspension to be shifted in the horizontal direction? Ball of mass m suspended by a thread of length L. With what minimum velocity has the point of suspension to be shifted in the horizontal direction? So, okay, like that. For the ball to move along the circle about that point. Huh? What? Shifted in the horizontal direction to point. They didn't even give us a figure. For the ball to move along the circle. I have no idea what they're talking about. Oh, okay. I think what they're saying is this goes like that, and then this starts going up. Okay. Well, I don't know. I don't know if this is actually going to happen. Think about it. So, so that it actually goes full circle. All right. I don't know what to do about this. With what velocity? Point of suspension to be shifted the horizontal direction. So there's no acceleration on this guy, yes, and it is moving like that. That's how it's doing. Alright. So the train is already taught. According to this guy, what's happening is that I mean, it's inertial frame, so still all of the laws of physics apply. And then what is happening is that this ball gains a velocity in that direction. Yeah, initially it's along that direction, exactly. And then yes, it changes as you put the tension force over here, it changes the velocity. Yes, all of that happens. Cool. The thing is, its initial velocity is that, and the tension force does no work on it because the string is inextensible and taut. So tension force does no work, and it just goes full circle. If it has to go full circle, then yeah, that makes sense. Fine. So at that moment when it's up, whatever its velocity is, call this thing v. It's in this direction maybe. This is u. So what can we say? I mean, acceleration is actually like there's tension force around there. You can just do work energy theorem. That's the best thing that we can at that point. And well, what else can we do? Oh yeah, so you can use that. So v squared upon L. That's just provided by gravity because critical condition. So no tension required, and then it's just gravity that's doing it. Yes, so that's G, and of course v squared minus u squared is equal to 2g h. Just work energy theorem basically. So h is 2l, so supposed to be 4g l like that, and then v squared just lg. So putting that over here, just get u squared is equal to, oh sorry, it should be negative. It should be negative. It should be negative. Yes, Now it's correct. And it's gonna be 5 lg. So u is just square root of 5 lg. So with that velocity, it should be yanked. Yeah. 137 got it. Square root of 5 lg. Man, this is the first time that I've actually done this kind of analysis, but I've not taken the space frame, but this frame of the actual point. Yeah. So it has to have velocity. Where did it go? So you didn't write a symbol for the main velocity. I'll just say v main is equal to square root of 5 lg. Nice. I'll remember that. 138. Because this is not just for this particular case, it's also for any kind of circular motion around on a vertical plane. That is, yeah. Let's go to 138. I mean, any vertical motion with a string, or I don't know, the normal forces involved, right? Yeah. So maybe this is going on a wall. I mean, it's not a wall, but this is how it is. It's going on this surface, and then in that case as well, for it to barely complete a whole circle, like over here, g should be the centripetal acceleration, and that's why square root of 5 lg it still works for this kind of thing, and for normal motion with a string attached, it still works. Okay, 138. A horizontal plane supports a stationary vertical cylinder of radius r, and it is A attached to the cylinder by a horizontal thread AB of length L0. So this is L0. Horizontal plane supports a stationary vertical cylinder of radius capital R. It's okay. This A. What? It's figure 1.32 top view. This is a top view. Okay. So this is a horizontal plane. This plane, the paper plane. Sorry, the screen is that plane, supports a stationary vertical cylinder of radius capital R. Okay. And a disc A attached to the cylinder by a horizontal thread AB. So AB is this thing. This is the disc A. Okay. An initial velocity is imparted to the disc as shown in the figure. How long will it move along the plane until it strikes again the cylinder? The friction is assumed to be absent. Okay. This is weird. So the stationary vertical, what? Stationary. Okay. Wait, okay, is this initially stationary or is it always stationary? They didn't give us any kind of masses, and that probably means that you can just assume this to be really, really heavy, and that would mean, yeah, it must be always stationary. Right. Friction is absent. Yes, good. It's not that bad, I think. Right. So now how do we deal with it? The tension force acting is what other force? I mean, yeah, like this is always moving with V naught. That's what we can say for sure. And we don't know what this path actually is. How does this get solved by work energy theorem? I don't guess it can. What's R, and I guess the only way to do it is using proper analysis of the motion. You can't just do work energy theorem over here because friction is absent, everything is absent, and no gravity, nothing. This velocity is constant. That's what we know. So with respect to this, right, with respect to A, how is everything going on? Okay, this is complicated. So A is rotating. Yeah, that frame will be rotating. No, that's just really bad. You can't do that. then the frame will be rotating and ah, this is just the worst. Come on, think. We wanna do it somehow. It's almost as if it's winding up. Yeah, this thing is rolling and that's how it's happening. Yeah, that could be a way to think about it. I just want to do that, right? I want to take that frame into there. So what we'll do is that we'll take a frame that is rotating as this thread is rotating, so with the same angle, and then it's centered around, I don't know, centered around this center of the drum or whatever this thing is. Yeah. So that this origin, it has zero velocity, right? But there's angular velocity. Yes. Uh, yeah. Do we know the angular velocity? Well, no. It just depends on the length, actually. Oof. Oh, come on. Think. Or let me just write the normal equations for this. Maybe that's the only way to do it. Just do it. So you got, I mean, initially it is not, okay, it's just like that. And let's say it winds up theta, okay? Then this is how it is. So r theta is this length, and this length is what is this length? Yeah, it will just be L naught minus r theta. And then this is still going with V naught, yeah, because work energy helps, so that's happening. Now you can think of it as momentarily doing circular motion about this point, yeah. Okay. In reality, of course, it's actually not doing that. It's slightly different than that. Ah, what is this? I mean, I just really wanna think of it as rolling motion. So this disc rotate, rolling as seen by this guy. I just want it to be like that. Okay, what angle is this? What is this angle? This angle is supposed to be theta, yes. So then you can do this, and it's 90 over here, so like 90 minus theta, and then it should be theta right here. So, oh wow. Then what that means is like d theta upon dt is just, so because it's about that point, right? So when it moves a little bit, just get that, and fine. So like d theta upon dt is just v naught upon this length, L naught minus r theta. That's probably what's happening. Is this correct? I don't know. I have no idea. Oh god, there's supposed to be like pseudo forces and everything active on it. This omega thing is like changing. Uh, uh, right. I mean, you could just analyze the same thing by doing that, different reference frame stuff. Yes. So that's the equation that we get. D theta upon dt is equal to v naught upon L naught minus r theta. And then we just integrate that. And when this completely winds up, we don't know actually what's going to happen, right? Yeah, we don't know what theta will get, but we will get your... So I should probably put this as capital R theta. So we will get L naught is equal to capital R theta. That's when this will happen, right? Oh yeah. Okay, we don't know what L naught is. Anyway, let's try to do it. Oof, let's try it out. So integrating, just get L naught theta. So initially theta was 0, so no problem. And then minus r theta squared upon 2. That is equal to, so v naught dt integration of that thing V naught is always kind of constant, so just V naught T. That's how it's gonna be. So what we want is the condition when L naught becomes equal to R theta. Yes. In other words, whenever theta becomes equal to L naught upon R, we just want to figure out when that happens. So you already got an equation giving time as function of theta. Just put that in there. So L naught squared upon R minus R, and these things like squared. So L naught squared upon 2R, wow, which is this thing, is equal to V naught T. So the time required is just L naught squared upon 2R V naught. And like hopefully it's correct. I don't know if there's more involved with than just that, because this is, yeah, right. What do I even say of this? Well, first of all, like the string cannot just bend awkwardly. So whatever velocity, I should not say that. Whatever direction the string was going, right, the same direction should just continue, and then you got get this thing. So that's why this angle is the same thing as theta. Just the tangential, just a tangent to that. Yes. And yeah, I mean this is approximately stays kind of constant. I mean, at least at this moment. Sorry, it's not staying constant. What I mean is angular velocity about this. For that, you just take this particular moment and take a very small time interval. So this is like omega is v naught upon this quantity, right? Because this approximately stays constant in that short interval. Yeah. So it just does this, and then you can figure out what this angle change is and everything. It works out, I guess. Yeah, I should do it. Okay, please don't. Please don't go away. Or maybe we could do, I don't know, complex analysis of this thing. We could actually. You know, there's this thing, there's this R, and you got this theta, and not bad. We could do it. So let's see if that actually gives us the same thing as well. So we'll just say this is the real axis, this is the imaginary axis. So this vector is just r e power I theta, and then this angle is 90 plus theta. So we'll just pi by 2, e power I pi by 2, just iota. Yes. And that's obvious. I'm just rotating 90 degrees. Yes. So this thing is just plus L naught minus r theta, and that times iota e power I theta. So now if I differentiate that, right? So I should just get velocity, and velocity is really just, well, v naught. And what is this angle that it makes with the real axis? So this complete angle, right? So it's just another 90 degree turn, because of course, yeah, that's 90 degree or 90 degree. Like that's theta, of course. So it's just negative. So it should just be negative v naught e power I theta, right? Makes sense. And the derivative of this thing, well, that's just iota r e power I theta, and then d theta upon dt is called omega. And then derivative of this thing, so you got that thing, L naught minus r theta times e power I, all that stuff, right? Yes. You should first of all take the derivative of that? No. First, we'll just do this thing, derivative of that thing. So it's supposed to be negative, and then you got omega, so not minus r omega. So r theta times omega. Then you got e power I theta, but negative of that thing. And then you also take the derivative of this. So from there, you just get negative r I e power I theta, right? Yeah. Now that times omega, because theta right there. So theta upon dt, omega. And that's why this cancels, and you still get the result that we got originally. Man, complex analysis is the way to go all of the time. Okay, cool. So you got it. Actually, what were we doing? We were finding time, of course. So this is a time required. Yes. Now get rid of everything else. Boom, everything else is gone. Then you just get the time is L naught squared upon 2R V naught. That's what you want to find, right? How long will it move until the plane strikes again? Yeah, it's length. So until it strikes it. Yes. So that will be this time. Let's write as capital T. So to 139. A smooth rubber cord of length L whose coefficient of elasticity is K suspended by one end from the point O, figure 1.33. Where? This thing? Okay. Smooth rubber cord of length L. Its coefficient of elasticity is K is suspended by one end from the point. Coefficient of elasticity is K? You mean the stiffness coefficient or what? I'm just gonna say it's a stiffness coefficient because I like it like that. Suspended by one end from the point O. Okay. Fine. Other end is fitted with a catch B. So, right over here. A small sleeve A of mass M starts falling from the point O. Okay, relating the masses of the thread and the catch. The maximum elongation of the cord. Huh? Uh-oh. But isn't there supposed to be like friction, and isn't that why it's not doing anything? Okay, what is this? Ah, okay, small sleeve A of mass M starts falling from point A. Is this not attached to it? Because only then can I figure out anything. Because I don't know, like what is the friction in it or what? What's the force trying to resist this? Because if there's no friction, it will just fall down like that. Oh, okay, it will. So the by catch, we mean literally something that catches A, right? So it will just fall down freely, and then it will hit B, and then it will keep on going, right? So mass of B is negligible, and that's why momentum of A will not change. It will just keep on going, and then after that, it's like yeah, it will do this thing and come back and whatever. So you want the maximum elongation of the cord. No big deal. No big deal at all. So the work done by gravity plus the work done by this string force, that should amount to zero because its changing kinetic energy is zero. So it goes from here all the way to that. Yeah. From point O. Okay, so it's complete length, huh? Well, that's a lot of velocity. Wow. So this is going to be mg L plus x is equal to half kx squared. Yes, that's how it should be. Huh, this wasn't that bad actually. So we just want the maximum elongation. That's it. X is what we are looking for. Oh no, it's a quadratic. Uh-oh. Are you serious? This is a quadratic. Am I supposed to solve this? Oh no. Fine, let's do it. Kx squared minus 2mgx minus 2mgl is equal to 0, right? So your x will just be negative b, so you got 2mg plus minus square root of b squared. So yeah, this thing squared. Let's take 2 out. Square root of b upon 2 square minus ac, just like that. So this mgx thing squares like m squared g squared x squared minus ac. So it's gonna do, well, this times that. Yes, so plus 2k mgl, and then this whole thing upon, well, 2 times k. Yeah, that should be the thing. So what will that be? So it's just I mean, seriously, what is this? Just horrible. mg plus minus, yes, but it's going to be plus. It's not minus, it's just plus, right? Maximum elongation. Exactly. There's also that other thing, the, you know, other, what do they call it? The other extreme point that it would have gained, right? That it would have gone to if like this string just kept on compressing, right? That would have happened if A tried to take B with it, but that won't happen again. So the negative version is just not good. That it doesn't even, I mean, give us the minimum value. Yeah, it's got a different motion completely. So just mg plus square root of m squared g squared. Why is there x squared? That shouldn't happen. It's supposed to be m squared g squared. Yes, no, not x squared right there. It's just mg. That's x squared. Yeah. Look at the units. It's got to be like that. Plus. So kl, that's like fourth. Then mg is also fourth, so it works out. We got this 2. It still stays over there. So 2k mgl, and then this whole thing upon k. I really wish, I mean, okay, what if I just take k in, right, into the square root? Yeah, that would not be nice. That probably won't be a good idea to do. So from mg upon k, that thing squared, and then plus 2 times of mg upon k times l. Yes, and then mg upon k. Or maybe I should do it. Let's just use mg upon k as, I don't know, something, call it mu. So this will be like x is equal to mu plus square root of, well, mu squared plus 2 mu l. Yeah, exactly. So just write that as the final answer. So x is equal to mu plus square root of mu squared plus 2 mu l, where mu is just mg upon k. Alright, so that's 139. Let's go to 140 now. 140. A small bar A resting on smooth horizontal plane is attached by threads to point P. Where is point P? Okay, cool. And by means of a weightless pulley to point B. Okay, possessing the same mass as the bar itself. Besides, the bar is also, so it is attached to P by what? By threads. Okay, then it's inextensible. Cool. Besides, the bar is also, oh, so in that case, like this can only go by circular motion, and fine. Attached to point O by the means of a light non-deformed spring and stiffness, okay, whatever. Find its velocity at the point when it is breaking off the plane. What? When it's breaking off the plane. Bar itself. But why? Why should it break? It is not deformed, right? Thread means of a weightless pulley to point B. The same mass as the bar itself. Man, what is this? Look, this is like threads and whatnot, and oh, okay. Thread PA having been burned. Of course. Okay, now I understand what's happening. The bar starts moving, yes, and then it's like this force. But this spring, okay, it changes its length. I mean, its orientation is also like changed. So is F equal to KX still applicable everywhere? What if this was some kind of wire? Then it would be applicable, right? Just like this is spring, and I think it will be deformed or something, whatever. I mean, it will deform in a very bad way, and it won't give non-linear So it will give non-linear forces and whatnot. So let's forget about that. Just go with the question. Thread PA having burned, the bar starts moving, finds velocity in the moment when it's breaking off the plane. This is hard. This kind of analysis is just so not good. So this will happen whenever the upward force is more than mg. So upward force is just, yeah, like, okay, let's do it. So this is point O. If this has moved by x, right? So this is A over here. Okay, no, let's use x to actually mean the deformation and not like that. Oh, come on. Or you know what? No, just use x. What the hell? Just use x. Or in fact, even better, just use some kind of angle. An angle is always better than using these kind of things. So we'll use this angle because initially it was 0. So we'll call this thing theta. Then this is 90 degree over here. So like this is L naught, right? This thing will just be L naught upon cosine theta. Cool. So you can figure out what the extension is from that. And this is 90 minus theta and whatever. Like this will be theta. Yes. So the thing is like K into L naught into sorry, it should be K. Why is this here? Stiffness constant K, L naught, all that stuff, like 1. And then there's the tension force over here. And yeah. Okay. So secant theta minus 1, right? That is the force put on by the spring. And now this times cosine theta is giving us the vertical force. So basically KL naught into 1 minus cosine theta is the vertical force. So whenever this becomes to mg, we are done. It just goes up straight away. Yeah, so you just have to wait till that point. And what do we want? Find its velocity at the moment when it is breaking off the plane. So whenever this happens. Okay, so basically it's just giving us what cosine theta should be. And now let's use the work energy theorem to get this guy's, velocity. Now the thing is, this has gone this length, so L naught sine theta on the front, right? In the right direction, and then because of that, B must have gone down, right? Yeah. So yeah, like this velocity, and there's velocity for B as well. That's the problem, right? B also has some mass, and this is complicated. So there's the work done by tension on B and the work done by gravity. So mgh, work done on gravity, work done by gravity on this thing, and then velocity we don't know. So you have to consider the whole system as one thing, and then figure out the work on that. Fine. So just got mg h is in this case just L naught sine theta. Okay, that's one thing. So that's positive work done on it. Then that's negative work done by the spring, so just negative half kx squared. The tension force does not do work on the system by itself because equal opposite, whatever. Yeah, I mean it's not equal opposite, but you get the idea that it's the same magnitude and that the displacement along the tension is the same. So sorry, along the, yeah, these are the same, but it's opposite. Yeah, you get the idea. Yes, minus half kx squared. So x is just, well, this thing. So that guy squared. Oh no, that's just the force. This is the displacement. So L naught squared, and then you got secant theta minus 1. That guy squared. Yeah. So this is the work done, all of it, right? Anything else? No other forces, and that's equal to what's happening? Half of mass. Oh, it's supposed to be mass B. Sorry. You know what? We'll just call it capital M. Yeah. So this will be small m plus capital M, where capital M is the mass of B. B squared, right? That should do it. Perfect. And now we can try to figure out everything. Oh, I wish we could say that. This is hard to use. Okay, think. What do they want? They want the velocity, right? I mean, this will give us a very ugly formula if we try to generalize. So let's just go with, calculation. Figure out what cosine there should be. Hopefully, it's some kind of good value, right? So what's K naught? Stiffness is, well, this is basically stiffness. 5 m. Oh wow, this is awesome. You see, okay, so you can just do that, huh? So what we'll say is like, okay, K is equal to mu, I don't know, mu, okay, whatever the symbol is, then mg upon L naught, right? With that substitution in there, we can just get, okay, 1 minus cosine theta is just mg upon L naught, and that upon K, it's like 1 upon this guy. Huh, yeah. Okay. Think about it. Yes, this looks correct. And then if you want to find out what this equation becomes, so man. Oh, and it also relies on the fact that capital M is the same thing as small m. So you know what? We'll just say okay, capital M is like small m times mu. Why am I doing this? Like this is so simple. We don't need to generalize this. You know what? Just skip this. Just skip all of it. Just skip everything. Don't generalize that. It's only 1 minus. It's the first time I'm saying this. Just don't generalize that. Mg upon KL naught is only 1 upon 5. So cosine theta is just, 4 upon 5. So secant theta is 5 upon 4. Sine theta is 3 upon 5. Cool. We got the whole family. And capital M is the same thing as small m. So just put that in there. Now it's just 2 times of small m. That's gone. Wow. Yeah, right. This upon m, I guess. Yeah. So now we use the fact that K is just where it go. 5 mg upon L naught. Putting that in there, just get 5g L naught. Yes. So this whole thing just becomes 5g L naught. So basically it just becomes negative 5 upon 2g L naught. Wow. Secant theta, that's 5 upon, like this minus 1 is just 1 upon 4, I guess. So it's going to be 1 upon 4 squared. I think so. Yes. That's what it's going to be. So 1 upon 16, huh? And then you got sine theta, which is just 3 upon 5. Just putting that in there. Oh, this is weird. Yeah, whatever. As if I really care about it. Yeah. So you got the thing. So from here you can figure out what v squared is. Let's calculate. V squared is equal to g L naught times. So it's 3 upon 5 minus, well, 5 upon 32. Cross multiply, it's gonna be, this is bad. This is a really awful value. No, you're gonna put half over there and whatnot. So L naught will be half, and g, let's just assume it's 5. So this quantity will just become like, okay, v squared is 5 times all that stuff. So it's gonna be 3 minus of 25 upon 32. Ugh, not good. Fine, so like 30 times 3. I mean, the upper number is gonna be odd anyway, so no hope for us actually. Did I do something wrong? No, it was just 2m over here. That m got cancelled, and then you got this thing. Yes. I'm tired. Fine. So just wrap this up with this calculation. It's gonna be 96 minus 25 upon 32, which is 1/772 upon 32. Not helpful. Square root of that thing. Whatever. So square root of, what was this? 71 upon 32. Most likely it's incorrect because I made some kind of error, but whatever. Meters per second in SI units. Wow. This is it. So yeah. I'll see you guys in the next video. Bye.